So in this lesson, we're going to continue our exploration of molecular shapes, looking at how molecules get their shapes, and this will include the introduction today of double bonds. I think everybody's familiar with the molecular formula for water, H2O. We could call that dihydrogen oxide. And since it's a covalent compound, that would be the proper IUPAC way of saying that. IUPAC stands for, and this is something you're going to need to know, International Union of Pure and Applied Chemistry. IUPAC, I-U-P-A-C, International Union of Pure and Applied Chemistry. IUPAC, International Union of Pure and Applied Chemistry. And that's the organization that actually decides whether the periodic table should be laid out. It decides on how the formal system we have for naming molecules or ionic compounds or just about anything. Anything that has to do with how chemists talk to each other, basically. IUPAC is responsible for that. So let's go back now and look at our orbital notations for hydrogen and oxygen and bring that forward to how we figure out the shape of a water molecule. So hydrogen is located in this region of the periodic table over here we call the S sublevel region. Okay? And it only has one electron. It's got one proton and therefore one electron for the hydrogen atom. And that's, since the one primary energy level only has an S sublevel, we only need one box in our orbital notation, and since it only has one electron, we only put one arrow in the box. And always it's the first an arrow that points up to start with. There are two hydrogen atoms in a water molecule, and then these two hydrogen atoms are going to covalently bond with an oxygen atom. And oxygen is in the second row of the periodic table. It's right here. And so we have the 1s sublevel is going to be full. It's going to have the S sublevel always has two electrons. We'll have two arrows in 1s. Then we'll have two arrows in 2s. This is the second row. And so the placement or where these two atoms are located, or these two elements are located on the periodic table, indicate to us that in the ground state we're putting two electrons in S here. Okay, and then where we're over here, where oxygen is, this is the P sublevel region. So over here we're putting 1, 2, 3, 4 electrons into P. So here's 1s, and there are two electrons, and then 2s, and two electrons, then 2p. And we need 4 electrons, 1, 2, 3, 4. Now you need to be very careful about how you figure out how many valence electrons there are. A lot of people got that wrong on the last test. There are not just 4 electrons in the valence level, there are 6. The valence level is the second primary energy level. So this big number 2 here tells us that in that highest energy level there are 1, 2, 3, 4, 5, 6 electrons. Okay? In order for the kind of bonding that takes place to happen for a water molecule, we have to hybridize the oxygen into the sp3 form. And so in the sp3 form then, 1s doesn't change, but 2s and 2p all combine together. So if you just look at the letters here, S and P, I can't really cover up the P without covering up the 2. We have one s orbital in that valence level and 3 p orbitals in that valence level. 2 just tells us that's the highest energy level, or that is an energy level, and the highest energy level is 2. And we're going to combine this 1s orbital and these 3 p orbitals here to make an sp3 set of hybrid orbitals. And so we're going to get 4 orbitals that are all hybrids, and we call these sp3s, and this is in the second primary level, the valence level for oxygen. And we're going to count all the electrons, 2, 4, 6 electrons here. and put them in one in each box and come back and pair them up as needed. 1, 2, 3, 4, 5, and 6. And so that's the hybridization for oxygen. That's sp3. Okay? And so what we have now is we have one electron here in hydrogen. Hydrogen only has an s sublevel, and it needs to have 2 electrons to have a full valence level. So this hydrogen then can share this electron with this oxygen in this orbital, and can share this hydrogen here can share this electron with this orbital of oxygen. So they're actually going to not just share electrons, they're going to share orbitals. And those orbitals are going to become a bond. And so our balloon models are actually showing what the shape of that bond really is. So previously we looked at the shape of these orbitals before there was any hybridization. And we had, in the case of the p orbitals here, we had double balloons. There's one p orbital, and there's another p orbital, and then there's a third p orbital that's swinging out toward you and kind of going back behind here. Okay? And then the s orbital was around it. And when you hybridize it to sp3, then you get 4 balloons, or 4 hybrid orbitals. Okay? And so that's the way these all change shape. 2 balloons become 1. The s orbital becomes one of these kind of balloons here in order for this kind of bonding to take place here. Okay? And so what we're going to be doing is going from this now to the actual shape of a water molecule. And since we're sharing 2 electrons here, then 2 of these balloons are going to become long sort of hot dog shapes where we connect the oxygen, which is right here, to the hydrogen, which is going to be out here on the ends of those. So the shape of the hybrid orbital gets changed when there's bonding going on, when there's sharing going on. They get sort of stretched out into a hot dog or wiener shape. But these 2 balloons don't change. They stay exactly the same because there's no bonding going on. These 2 sets, these unshared pairs of electrons, remain unshared, and so the shape doesn't change. Now if we're doing the electron dot notation, which then becomes Lewis dot and Lewis formulas, then oxygen has these 6 dots arranged in this way. Where you put 1 dot on each of the 4 sides and go back and pair up 2 in order to get up to 6. Hydrogens have 1 electron dot. So there's the electron dot notation. When we show how they can share, much like I showed how they shared up here, okay, then we put those actual electrons actually in the same orbital. This gets that would actually fill up, take this electron and put it down here and put it in that orbital, but then this orbital is also part of that orbital. 2 became 1. Well, that's what's happening here. 2 balloons become 1 when those electrons get shared, and the shape's a little bit different. Okay, now that's when we show this sharing this way, this is called the electron dot, this is called the sharing arrangement. We start out with electron dot notation or electron dot formulas. Now we have a sharing arrangement. And now we're going to go to the Lewis dot formula. And there's the Lewis dot formula where the electrons that are shared get squeezed in between the 2 symbols for the elements. And finally we go to the Lewis formula, which replaces shared pairs and only shared pairs with lines. But these 2 dots here, those 2 pairs of dots there have to stay there because those are unshared electrons. Here are the unshared electrons here, 2 sets. Here are the unshared electrons, 2 sets. And they're going to remain in this single balloon shape over here. Okay? All right, now let's look at how we can figure out the actual shape of this in 3 dimensions. Okay? So if we have, going back to this shape here, this is our Lewis dot formula. Okay? We're going to count the number of sets of electrons around that central atom. Sets are all the electrons that are either lone pairs. So this is a set because it's a lone pair. Unshared pair it's also called. This is a set because it's a lone pair or unshared pair. This is a set because it's a shared set. And so when we get to double bonding, you'll have 4 electrons that become a set. And when we get to triple bonding, there are 6 electrons that are a set. So all the electrons shared between any 2 atoms make up a set and so do the electrons that are lone pairs. Okay, so this is 4 sets. And so what we want to do is to figure out, well, what shape will allow me to get those 4 sets of electrons as far apart as I can while still be attached to this oxygen. Okay, and that's called a tetrahedral. It's 109.5 degrees excuse me, between the axes. Remember when I did the needle through the balloon? I showed you what that axis was like. Okay, so here's an axis going up to one of those sets of electrons. Okay, and here's an axis going to another set of electrons. And the distance between these two angles, actually I've got it a little wide here, it should be a little closer together, but it should be 109.5 degrees. Okay, that's the angle. And in order to get in 2 more angles from these other 2 sets of electrons up here, I need to have one swinging out toward you, and we show that with a triangle shape. Okay, and so there's a set of electrons. And then to show one of these going kind of back behind the paper, we're going to use a dotted line to show that. Okay? And that's a 3-dimensional shape that we call a tetrahedral. Now, since all we have are electron pairs on the periphery here, we're going to call this, we're going to give it a special name. This is going to be called a tetrahedral. Anytime you have 4 arms around a central atom, spaces equally apart, it's called a tetrahedral.
So what is can you remind me what that triangle is?
That tells you that this set of electrons isn't going out straight on this paper. It's swinging up toward you like this. Does that make sense? What I just did?
How do you know that?
Hmm?
How do you know that?
Because that's the only way you can get all these 109.5 degrees. At 109.5 degrees, if I had 109.5 degrees flat on the paper going to here, well, then I couldn't fit this one in at 109.5 degrees. In order to get 4 things around a central atom equally spaced flat on the paper, it has to be 90 degrees. And we have to have more space in it. What we're doing is trying to get them as far apart as possible, and 2 dimensions don't make it. We need to have 3 dimensions here. So we're going to start thinking in 3 dimensions. Say what now? This balloon here is swinging out toward you. This set of electrons here is swinging out toward you. Okay? All right. So that's a tetrahedral electron pair shape.
Will it always be 109.5 degrees?
If there are 4 sets of electrons around that central atom, when you get to this shape, not the molecular shape, now when you get to this shape, okay? When you first go from excuse me, Lewis dots to the first 3-dimensional drawing, if there are 4 sets of electrons around that central atom, then that will make a tetrahedral. It will be 109.5 degrees. Not all molecules have that angle because some of them don't make tetrahedrals, don't have 4 sets of electrons. But we'll get to that. Okay? All right, now from there then, we're going to replace 2 sets of electrons with 2 atoms because that's how many are shared. Over here in this drawing, this Lewis dot drawing, we have 2 hydrogens sharing electrons with oxygen. So there really are, instead of these 2 electron pairs here, which look like lone pairs, okay, they're not attached to anything, we're going to replace those with the hydrogens because that's what's actually there. So from this shape, this tetrahedral electron pair shape, we're going to redraw that same shape. Now this is where you want to do this in pencil, guys. You're going to find that's going to be helpful. Okay, because this is one of those things I warned you earlier in the class several times that we're going to be doing things where I expect you to erase stuff. Okay? And this is one of those cases where I expect you to erase things. So what you want to do is to redraw this exact same drawing. Exactly the same, with exactly the same angles. Okay? And then go up here and look and find how many sets of electrons are actually shared as these 2 right here. This is shared, this is shared. How many are shared, and replace those dots then with the element symbol. So now that's where we erase these and replace those with the element symbol. So now we took this tetrahedral electron pair shape and we modified it. And that's what we're going to call this, a tetrahedral modified electron pair shape. Okay, last step then. We're going to take this shape and redraw it exactly as it appears here again. Okay, remember, do this in pencil. Okay, so you got your oxygen in the center. You've got a hydrogen, in this case, going up. Now the hydrogen could be out here on these arms. It doesn't really matter which arms you put it on. I just happen to put it on this arm and this arm. And this one going here. And then we got an arm that's swinging out toward you, and use that triangle shape for that. And an arm that's swinging back behind the paper. And that's what that dotted line means. Okay? And then what you're going to do is, after you redraw exactly the same shape, you're going to erase any lone pairs. Okay? Erase the lone pairs. Now, why do I have you draw it and then erase it? Because I've been doing this a while. And I've seen students try to go from this to this without first drawing in the lone pairs, and they often get it wrong. But if they draw the lone pairs and then erase, they don't get it wrong. Okay? So it's just a tool. You want to get it right, or you want to take a chance on getting it wrong. If you want to do well on the test, you'll do it the way that I teach you to do it. Okay? It's just shown, it's been demonstrated over and over. Students get it right when they do that. Now, some students will get it right. Don't bet that you're the one that's going to get it right. Okay? Don't take chances. All right? So, this then is the actual molecular shape, but it's not tetrahedral anymore, because a tetrahedral has to have 4 arms, equally spaced, 109.5 degrees. This is not tetrahedral anymore. Okay? It's still 109.5 degrees from here to here, or roughly that. It's actually slightly less than that. We won't worry about that. So it's slightly more than 90 degrees. Okay, almost 10 degrees more. All right, not quite 120. Okay. All right. So the name of this then is not going to be a tetrahedral. Okay. This is a really high-end, guys. This is going to be a hard name to remember. It's tough. Okay, so you might want to write this down. Yeah, I'm joking. Yeah. Okay. So a bent molecular shape. That's the actual shape of the molecule. Usually I get at least a chuckle out of that, but must be Monday and you guys are just not, into anything here. I mean, my jokes are just that bad, huh? Okay. It's not Monday Fun Day? Okay. All right. Now, you should have done a balloon model, okay, on your own, where you did ammonia, right? And so I want you to go through the same process for ammonia. We'll make that part of your homework, okay? Homework. And we'll probably add some more homework to this before the day is over, but draw a set of 3D shapes for ammonia. And ammonia is NH3. Okay? So you're basically going to go through the same set of steps here, okay? You'll start out with electron dot notation, then Lewis dot. You really don't need Lewis formulas to go through this, okay? You can stop at Lewis dots, but then you're going to go through these 3 steps on your ammonia shape. NH3. Last week's balloon shapes were the sp3 hybrid orbitals without any bonding, and the methane molecule. Okay. Did I give you all? Did I draw methane out for you guys like this? No. All right, I'll do that right now, and then we'll move on to our next model. Okay. But for your homework tonight for this ammonia molecule, then you've got to have this shape. You've got this drawing, then this drawing. You've got to have this drawing for ammonia, not for water, but for whatever ammonia happens to be. This drawing, and finally this drawing. Okay? So you got to have at least 5 drawings, if not more. And don't skip steps. Skipping steps, I've just seen it, not good. All right, now, just before we go on to our next thing, which is to do the balloon model for water, let me show you methane here real quick, just as another example, because something different happens for methane in this process, okay? So here's carbon, which has 4 electron dots, and hydrogen, which each hydrogen has 1 electron dot. Okay? And we're going to share electrons, and what we're trying to do is to get, even up here, we want to get oxygen to have 8 electrons around its outer energy level. So 2, 4, 5, 6, and then we share 2, that gets to 8 in the valence level, it's called. The outer energy level is 8. And we do it like this, we still get to 8. 2, 4, 5, 6, 7, 8 electrons. So oxygens have 8. Hydrogens need only 2 to get to their full valence. And so what we're doing here is to get the carbon getting up to 8. And so it started out with 4, sharing 4, it gets up to 8. And each hydrogen has 2, which is all it needs. So there's our sharing arrangement. And then we got to have the Lewis dot formula. We squeeze the electrons in between the element symbols, and we've done that before. But then we're going to look and see that I have 1, 2, 3, 4 sets of electrons. In this case, all the electrons around carbon are shared. And all the electrons shared between 2 atoms make up a set. That's 4 sets. So for 4 sets, then, of electrons around a central atom, or an atom of interest in a larger molecule, that's a tetrahedral arrangement. It's not always a tetrahedral, but it's a tetrahedral if I have 4 sets of electrons around a central atom or atom of interest. Okay, and so we've got electron dots in this tetrahedral electron pair shape. And then the next step is to go and replace any sets of electrons that are shared. Well, how many sets of electrons are shared here in this Lewis dot formula? Huh? All of them, all 4. And so now we're going to go through, draw exactly the same shape again. Remember, that's what you have to do, draw exactly the same shape again. Put your and do it in pencil, because this is one of those cases where we talked about this year where erasing is going to be necessary. Then go through and replace those electron dot drawings with the element symbol if they're shared. And all of these are shared. So we're going to replace that with the symbol for hydrogen on all these 4 arms in this particular case. Okay? Now, if you notice, we never got a modified electron pair shape. If there are no lone pairs, there will be no modified electron pair shape. Okay? If there are no lone pairs, and there are no lone pairs here, then there's no modified electron pair shape. We went straight from the tetrahedral electron pair shape to the tetrahedral molecular shape. We didn't change the shape. The shape stayed the same. All we did was replace electron pairs. So this is also a tetrahedral molecular shape. Okay? There is no bent for methane, because bent only occurs when you get rid of these 2 electron pairs over here. And your molecular shape for ammonia will be neither tetrahedral or bent. It'll be something new. Okay?
Now does that, the triangle, does it matter where that triangle and that dotted line's at?
You mean as far as being on this side or the other side?
Yeah.
No, because I did it up here on the other side. It's fine. Okay, as long as you have these 2 at about 109.5, about 110 degrees here, and these 2 over here on this side, or flip it around if you want to. Okay, it's fine. Okay? Okay. Now, going back to water now, we're going to make balloon models for water. Okay? So how many round balloons are you going to need for this molecule? The lone pairs are round balloons. How many round balloons do we need? 2 round balloons. And the long balloons with the little hydrogen thing on the end, we got how many of those are we going to need? 2. So there's 2 here for hot water, okay? So make your water molecule balloon model, please. All right, guys. Once again, you got to make sure you label everything. So these little round balloons on the end, those represent our hydrogen atoms. Okay? The hybridization on this oxygen atom in the center of our water molecule is sp3. And so down here where the oxygen is going to be, you can label that as sp3. And anytime you have 2 electrons shared between 2 atoms, directly in a line between 2 atoms, or anytime you have a bond that involves a hybrid orbital, that's going to be a sigma bond. And so the sigma symbol is kind of an O with a kind of a pompadour swish. I don't know if you know what that is. Okay? And your round balloons are unshared or lone pairs. And you can label it either way. I'm going to label them both just to show you can label them both. Unshared pairs. So in our models, this lone pair is like 2 big dots, if you want to do that. Okay? So just as before, you're going to take your balloons and tie them together. It's usually easier, not necessary, but easier to tie your 2 long balloons together first, and your 2 round balloons together as a separate thing. So these get tied together, and your round balloons get tied together. And this is just a square knot. It's just like tying your shoes, but without the bunny ears to tie your shoes. And then these 2 sets get put together to make your water molecule. Okay? And then we want to cut one of these things off because you only need one to tie your string to carry it around with you. And you can tie a string to this, and that's carrying it to carry your water molecule around with you all day long. Okay? These unshared or lone pairs, those are also sp3 hybrids because we hybridized all of the s and p orbitals on the oxygen. So we need to make sure you label the unshared pairs as sp3 hybrids as well. Okay? Okay, sp3.
So the 2 dots are because these have 2 electrons, right?
Well, you don't have to put the dots in there if you don't want to, but I think it's a good idea. But you definitely need to label this as sp3 because that's what it is, an sp3 hybrid. All right, just to make sure we're as clear as we can be here, this is a 3-dimensional shape for a water molecule. Okay, 3 dimensions. If you flatten it out like this, now you have the shape as it appears when we draw it on paper using those line and dot formulas, okay? Where we have things that are 90 degrees to each other. We can flatten it out that way. We can kind of flatten it out this way, all right? And we get the same kind of shape you get on paper when we draw it. But in fact, it's in 3-dimensional space. It's going to look more like this. And that's the point of doing these molecules, these models, so that you can see for yourself what the molecule looks like in 3 dimensions. All right, guys, we're about to move on to something else, but let me just show you something real quick. You need to draw the shape of your balloon model in your notes. But looking at this model here, this is our tetrahedral modified electron pair shape, and that most closely corresponds to your balloon model because you've got 2 round balloons that represent the placement of these 2 lone pairs over here in this 3D drawing. So if this is our oxygen at the center here, and I've got a balloon here, and another balloon sort of in the back, like that, and then I've got this round balloon like this, that's the bond going to the hydrogen, and a long round balloon like this, that's going to the other hydrogen, okay? And so all of these are sp3s, and so you need to label yours as being sp3s. This is what you need to do in your notes. These are also sigma bonds, and these both are lone pairs. Or unshared pairs, you can call them, if you want to label it that way. And you probably need to put 2 dots on both of them to show you have those right there, but I need to label all these this way. Okay? Now, we're going to move on from this, and we're going to talk about double bonds now. Okay? We'll talk about double bonds. We've been talking about everything we've been doing so far has been single bonds. So you need to get out your notes now. You can finish. If you're not quite there yet, you can get all this caught up here in a few minutes. Right now, we want to talk about what are called double bonds. Okay? Now, double bonds come from orbitals that are not sp3. Double bonds have to have at least an sp2 hybridization. So the first example we're going to do here is for 2 hydrogens, 1 carbon, and 1 oxygen. Okay? 2 hydrogens, 1 carbon, and 1 oxygen. So hydrogens, remember, have only 1 electron. So both the hydrogens have just 1 electron. The carbon has 4 electrons in the valence level, but we need to hybridize the carbon to sp2, not sp3. Okay? So let me start over here with the unhybridized set. Okay, so that's unhybridized. When we hybridize to an sp2, we only hybridize 1 s and 2 p. So only these get hybridized, and the 2p over here is unhybridized. So the result is our sp2 hybridization. 1s is not hybridized, so it stays the same. The s and 2 p's get formed into a new set of orbitals we call sp2s, because we started out with 1s and 2 p's being hybridized. We're not talking about the second primary level. Okay, this is the primary level. sp2 comes from 1 s orbital and 2 p orbitals being hybridized. And then the p orbital is not hybridized on the end over here. This last p orbital gets left alone. And then we count all the electrons in the valence level, 1, 2, 3, 4, and put them in each of the 4 orbitals, and then pair them up if needed. 1, 2, 3, 4. Each of the second primary level orbitals when they're hybridized, okay? All right, so oxygen works the same way. We start with oxygen being unhybridized over here. And oxygen has 4 electrons in 2p, 1, 2, 3, 4. And we hybridize that as well to sp2, so we're only going to use 1s and 2 of the p orbitals, okay, to get our hybridization. So we're going to hybridize one s and two p's. And we're going to have a 2p orbital that's left unhybridized over here. Count all the electrons: 2, 4, 5, 6. 1, 2, 3, 4, 5, 6. And that's what the sp2 hybridization looks like for oxygen. Okay. Now, what happens is these two hydrogens then can share their one electron. This hydrogen can share its one electron with this half-full carbon orbital. This hydrogen can share its one electron with this half-full carbon orbital. And then this hybrid orbital here can share with this hybrid orbital, and this unhybridized orbital can share here. And the reason we have to have an unhybridized orbital is I can't put two bonds between hybrid orbitals between the same two atoms. There's no space available. Okay, remember, electrons can't be in the same space unless I have them opposite spins or quantumly entangled. Okay, so once I get two in the same region, that's directly between the two nuclei here, the other set of electrons have to be somewhere else, and that's where the p orbital comes in. So if we look at the electron dot formulas, here's hydrogen, here's another hydrogen, here's carbon. Oh, I need to do it like without that second one up there. That shows 5 electrons, so let's get rid of that one. And then oxygen has 6. And so when we do the sharing arrangement, thank you. There's our double bond. 2 electrons shared, 2 pairs of electrons shared between 2 atoms. So the Lewis dot formula then looks like this. So here are the 2 hydrogens shared here and here. But there are 4 electrons shared between the carbon and the oxygen. Okay? I can do the Lewis formula, but it's not really necessary to do that in order to draw the 3-dimensional shape. But there's the Lewis formula. From the Lewis dot formula, I'm going to count the sets of electrons around the central atom. How many sets of electrons do I have around that central atom? It's the atom of interest here. It's all the electrons that are shared between 2 atoms make a set. How many sets? 3. 1 set, 2 sets, there's the 3rd set. That's all the electrons shared between these 2 atoms. Okay? So for that, we don't want a tetrahedral because I only have 3 sets. What angle between sets of electrons will get 3 sets as far apart as possible? If all the way around is 360 and I divide by 3, what do I have? 120. Right. Well, we only have 3 sets. No, we need 3 sets. Let me show you. Here's oxygen, and the far apart as you can get between these 3 sets is 120 degrees for every set. Here's a set of 2. Here's a set of 2. Here's a set of 4. So all of these are 120 degrees. Okay. And this is what we call. This is our electron pear shape, but it's not a tetrahedral. Okay, we will call this trigonal planar. Trigonal planar. And that's an electron pear shape. Now from there then we're going to replace all the sets of electrons that are shared in this drawing, and we're going to replace all the electron dots that are in this drawing that are shared, only those that are shared. So here's our oxygen, here's our 3 arms, here's our electron dots. Okay, these single pairs here, both the single pairs are shared with a hydrogen. So we're going to replace those with hydrogen. Okay? And the double pair over here is what's shared with the oxygen up here. So that's going to get replaced with the oxygen. Oops. I'm sorry, this should be a carbon. I don't know why I made it an oxygen. Carbon's in the center. So let's take out that part right there. Make it a carbon, okay?
How do you determine that it's carbon?
Because it's in the center here. It's the one that everything's attached to. So you have to choose the atom that everything is attached to be your atom of interest, or the one in the center. You call it your central atom or atom of interest. So we get to really larger molecules. We won't in this class get to larger molecules, but in the next level of biology, the next level of chemistry, you may have to do that. Okay? All right, and especially when you go to college, if you're going to take anything that has to do with medicine or the sciences, you're going to have biochemistry probably, and so you'll need to know how to figure that out, or even organic chemistry, you have to know how to figure it out. Huh? Okay, there you go. All right. So this then is a molecular shape, but it's not a tetrahedral. It's still the same shape as this. So what's this shape called? Same shape as this. What's it called? Trigonal planar. But this is the molecular shape.
So why is it not a tetrahedral?
Because a tetrahedral would have 4 arms equally spaced. This is 3 arms equally spaced. That's a trigonal planar shape. All right. Now, making a model of this is a little bit trickier because this double bond doesn't look like the single bonds. Remember, the single bonds were single balloon shapes, right? Single bonds were single balloon shapes. Okay? I have to have 2 separate bonds between 2 atoms to make a double bond. And let me show you how that looks. So here's our carbon atom, and here's the oxygen atom. And the first bond can be a sigma bond. So the bond between the 2 hybridized orbitals, that's a sigma bond. And it's going to be directly on a line between the 2 nuclei. That's our Wiener shape. Okay? But the second bond can't be in the same space because I can't put more than 2 electrons in the same space. I can put 2 electrons in the same space because they have opposite spins, because they're quantumly entangled. But after that, I've got to put the second set of electrons somewhere else. And that somewhere else is above and below. That somewhere else is going to be above and below. So the second bond here, called a pi bond, has 2 parts like the original p orbital. The p orbital, remember, had two parts? Well, we're going to take those p orbitals on this on this carbon here, the unhybridized p orbital. So we have a p orbital on the carbon here, a p orbital on the oxygen here. Okay, so they're unhybridized. They're in 2 parts. And those parts are going to reach out and join up with each other, top and bottom. Okay, so what we're going to get when we're done is something that looks like this. All right, and that's what our double bond looks like. Now, the thing to remember, the tough thing for students to apparently grasp is that these 2 parts, top and bottom, those are not that's not 2 separate bonds. The top and bottom part is all one bond. Top and bottom part is all one bond. Okay, so all that right there represents a one single together pi bond. Okay? Pi, just like pi in math, okay? A pi bond. This in the center here, that's a sigma bond because it's directly on a line between 2 nuclei, and it's also the sharing of electrons between hybrid orbitals. So sigma bonds come from sharing electrons between hybrid orbitals. Now, the oxygen over here has 2 lone pairs of electrons. Well, that's a couple of round balloons. Those are the unshared pairs over here. All right? Those come from hybrid orbitals because there are unshared pairs right there in hybrid orbitals. Okay? We hybridize those to sp2s. Unshared pairs are always hybrid orbitals. But then I've also got 2 electrons that are shared between this carbon and this hydrogen. So we've got 2 of these Wiener shapes going out here to a hydrogen atom. And in our balloon models, we always made that as a little round part on the end. Does that make sense? That's a complex model, isn't it? All right. Well, because we're running out of time here, that's going to be your homework. So let me explain one thing about making these models that will help you a lot. The pi bonds are sigma bonds that don't have a hydrogen on the end. Pi bonds are sigma bonds that don't have a hydrogen on the end. I'm trying to find my long balloons here. Okay? Before you blow those up, pi bonds are sigma bonds that don't have a hydrogen on the end. So here I need something to tie to make a knot right there where the oxygen is and put 2 round balloons on it. So before you start blowing those up, now these over here you blow up, make a little round balloon and tie it off, just like we did before. But these right here, you're going to tie a knot in the end before you blow anything up so that you'll have something to tie with. Does that make sense? So that'll allow you to tie right here, and then you can blow up a balloon and make the Wiener shape here, or you can make this. Now with this, you blow up a section that's longer than your sigma bond. This is, say this is 9 inches, you want this balloon 12 inches. That makes sense? About a third longer. Okay? This is 9 inches, that's going to be 12. If you make this 10 inches, you need to make that one about 18. Okay? So you're going to blow it up, tie a knot, blow it up a second time, tie it off, then you can tie everything together. Does that make sense? Got it? Okay? So that's your homework tonight, to make this model. Okay? Well, I can make this with 1, 2, 3, 4, 5 long balloons and 2 round balloons. But you don't have to make it with that number. You can make it with something else. Yeah, well. This video right here? Yeah.
What do you mean?
Okay, so if you're struggling with how to make models of double bonds, well, you probably want to look at, there's always a video for it. So here's this video. This title of this video is Unit 3, SP2 Hybridization. And you should find that in the playlist for molecular models and or molecular shapes. And so this is Unit 3, SP2 Hybridization, and it'll go through how to make these models that have that second balloon in the pi orbital form. I'm trying to scan through here. There it is. There's a picture of it right there where I'm showing how that balloon makes that loop right there. Now this model here is not, may not be the model that you were given to do, but this is a model that shows a pi bond. Pi bonds are in 2 parts, top and bottom, around a sigma bond there in the center. Let's see here. There's another type of model for a different molecule that has a pi bond around there's a pi bond, the red balloon, there's a pi bond around a sigma bond in the center, there's a sigma bond in that yellow balloon shape. Each of these balloons out here on the ends represent sigma bonds as well.